Hello everybody, good morning. We are starting our last lecture this year, so welcome. And this lecture would be on several topics. First, we would investigate the situation on a transmission line that is loaded by an impedance, let's say arbitrary impedance. And we will find out that one of the miracles of radio frequency circuits is that what you see is not what you have. To decrypt it, we will talk a little bit about transmission line and transforming of impedances. The second point we would do then, we will talk about impedance matching, which is an important job of a radio frequency engineer. That's not that important, or not in this sense, with heavy currents, although impedance matching is still important to get maximum power in the load. And then we will possibly have some more time, and that would be devoted to waveguides if we will be so effective that we reach that point. On the other hand, we still have one lecture in January, which most likely would be about waveguides, and at the end of the last lecture we would have a small repetition of the whole topic of all topics within this year. At the same time, there will be an examination this Friday for those who are in a hurry. In order to subscribe for the examination in COS, you should have Zapochet or assessment from Professor Machach, which I think he would put into the system after today's seminar. But please ask him, because this is the faster way. Otherwise, he normally would do that in the last week of the term, which is at the beginning of January. And now we are about to start with transmission lines. So what is the strange thing about transmission lines that are so long that the length is comparable to wavelength? Well, that is an important point. Just imagine you have a transmission line, so this is the line, and it is loaded by an impedance. This transmission line has a characteristic impedance which I would call Z0. We know that the characteristic impedance is a ratio between voltage and current of a line, of a wave that is propagating along the line. We might measure voltage and current in phasor form. We will get the complex impedance, and this impedance is the ratio between voltage and current of a single propagating wave through that line. Now, we would have the line loaded but by a loaded impedance ZL, Z load. In the case that this Z load is the same value as the impedance of the line, characteristic impedance, then we would have no reflection, and it's not very interesting. Because, as you remember, we have the reflection coefficient, let's call it R for voltage, which is Z load minus Z 0 divided by Z load plus Z 0. That's just to remind you of something that has been 2 lectures ago. But now we have this impedances and the reflection coefficient, and we have both waves, one coming there, one returning back. We have been investigating that wave shape a week ago. We called something like partial standing wave and a propagating wave. But the important point what we can see is Let's say that we have here the conditions at the load. There is an incoming wave and a reflected wave. And those together match the load impedance so that the voltage and current at this load impedance have the ratio of ZL. Now, if you would watch this from some distance, some length L, you would have a different condition. And that condition would differ in that you moved some distance. If the transmission line has a propagation constant of beta, it's a lossless transmission line, then at this moment the wave traveling there has, let's say, an equation of, let's call it V plus, like last week. So we would have a V plus as a function of distance z, and that is V at z0 times e raised to minus j beta z. So the coordinate z has a 0 at the place where we measure this voltage 0. And we have a reflected wave back, which is denoted by V with upper index minus. It's again a function of Z. It's again a phasor. So I will make hats over that a little bit later. And that is again given by the value of the voltage wave at Z equivalent to 0 times, but now the propagation direction is opposite, so we would have plus beta z in the exponent. And yes, we know if we put 0 coordinate just to the load, we know that the ratio of those two voltages is just exactly the reflection coefficient. Now, to be sure, I would mark all values that are phasors by a complex or by hat. Impedance is not a phasor, but it is a complex number. Reflection coefficient is not a phasor, but it is a complex number. And now, if we watch the phase difference along this line, we can see that one wave decreases its phase by beta z, the other increases its phase by beta z. So the phase difference between those two lines, or the phase shift, is changing by 2 beta z. So in fact, if we have a load with some reflection, then this reflection would be observed with different phases along the line. This is strange. We are used to have a voltmeter. We take the leads, we just put it to the resistor or transistor, and we see the voltage. Now this is because the frequency is very low, or the wavelength is very high, so that the length of those two wires we are using is so small that we do not count it. But if you have a transmission line, if you have the distance between the voltmeter and the load comparable to wavelength, you would see funny things. So what this does mean, for example, in a complex plane, if we had a complex plane, so we have the imaginary and real x, and we would like to observe the reflection caused by the impedance, well then with passive impedances we will easily find out that the reflection coefficient could be at maximum 1. Because was it higher, bigger in magnitude, it would mean that more energy is reflected than came from the wave. So that would be a source of energy. With passive loads, you can get at maximum the reflection of the same magnitude. So that this coefficient, the reflection coefficient, sometimes also denoted as big gamma, is as to the magnitude at maximum 1. So we possibly would be somewhere in the region where, so this is J, this is minus J, this is 1, and this is minus 1, the real axis. Somewhere bound in there, we would have all the values of possible reflection coefficient that could be achieved by passive loads. And now we, for example, put a 100 ohm load onto a 50 ohm line. So if that is 100 and this is 50, let's count with me. 100 minus 50 is 50, and denominator 100 plus 50 is 150. 50 divided by 150 is 1/3. So this line with a real characteristic impedance of 50 ohms loaded by a real impedance of 100 ohms would result in a reflection coefficient of 1/3, just here. Okay, so this is the situation. We have the voltmeter or the impedance meter, and at this frequency we measure it just at the load impedance. Now let's have a special voltmeter, special cutting voltmeter. We would have the line of 2 wires, for example, and the voltmeter is so strange that it runs through, it cuts the line, it measures the current, it measures the voltage, and once it moves, it again so does the line and just moves. So the line is intact, just the voltmeter is capable of measuring voltage, and at the same time it cuts the line and it's capable of measuring current. Or let's say it uses some kind of clamp current or meter which does not destroy the line. So we can measure voltage and current, and we would just slide along the line. So what if, for example, we slide for, let's say, 1/4 wavelength? And if this is a 1/4 wavelength, the phase difference between the incoming wave and outgoing wave is 1/4 and 1/4. So we would have 2/4 of wavelength, which is 1/2 of wavelength, which means that we have just antiphase. So 1/4 wavelength from there. Those two voltages and current would result in a reflection 1/4 wavelength from this load. We would measure again a real load, but at this time it would be in opposite phase. So the magnitude did not change, we have an opposite phase, which is a different load. But this is not the most funny thing about that. Just imagine that I have been moving somewhere in between that, and at the moment, at any point, the magnitude of the reflection would be unchanged. That's given by the conservation energy principle. But the phase is changing, and in between here, the result is that we have some imaginary part of that impedance. And we will soon learn what that does mean. Just we have created a load that is not purely real. using a real load and a shift along a transmission line. And if we now just have the crawling voltmeter and move again 1/4 wavelength, we will run through a whole set of impedances or reflection coefficient, and resulting point would be again at this point. So if we move again a 1/4 wavelength, we would get to 1/2 wavelength from the end, and the whole thing repeats. Each half wavelength we would have the same situation on the line. Now, in fact, what we can see here is a plane which describes all possible reflection coefficients. So I should possibly make a circle here. So we have a set of circles. Those circles show us the magnitude of the reflection, and of course we can see the angle of the reflection just on this graph. Now we can easily get a reflection coefficient with any phase just by putting a real resistor on the end and moving a little bit, moving properly. So if we would like to have this angle, we would just have to put the resistor and move this long. This angle would be, let's call it alpha, and it is 2 beta L. So if we know the propagation constant beta, we could easily find out how long line should we put in cascade to the impedance to get proper reflection coefficient at the input. There are several special cases I would like to show you. For example, we have a reflection coefficient of -1 over here, and this is a pure, and this is something which is a pure short. Remember, if Z load is 0, then we would have the coefficient of -1, so this is a pure short. Well, that's nice theory, but what, for example, if you have two wires and you have to short them, you want to make a perfect short at the end? Well, in fact, you have to put some conductor in between those two wires, like this. So you have a perfect short over here. But this is of some length. What would happen if you have a perfect short here and you observe it from some distance? Well, okay, the perfect short would be a little bit rotated in this graph, so what you would see is not a perfect short, but this. It is close to a perfect short, but it's not a perfect short. Well, in fact, this impedance would be not 0, but would be imaginary. And what is the imaginary value significance? Well, okay, we have, if the Z is purely imaginary, we could interpret it like J omega L, where L is an inductance. So in fact, any short current path which intended to be a short is in fact a small inductance. And a small inductance is something that could be dangerous. Let's say, to have a small example, let's say at frequencies between 1 and 25 gigahertz, you use packaged semiconductor devices quite often, like transistors. Such a transistor, for example, there is a PM from HP or Agilent today. It's something like a small ceramic hexagon. This is 1.8 millimeter. And this small hexagon has the chip inside, and then it has got some leads. So we have got 2 leads for emitter, which is a sheet of metal of, let's say, 1 millimeter in width. Those emitter pads are doubled on both sides, and then you have a collector, which is a very thin. It's not a wire. It's let's say it's again a thin sheet of metal, and the emitter, gate, is mostly made this way so that you can distinguish which is which. So this is 1.8 millimeters, so this whole thing is not very big. But now you have the printed circuit board, or let's consider that, to make it simple, this is the board, so the transistor is on one side. And you want to connect it somehow. And mostly this is used in microstrip circuits, so you have microstrip is such an arrangement when you have ground on one whole side of the board, and now you have to connect somehow the transistor down. So the simplest way you would use is you have the transistor, so you drill 2 holes and put those emitters that should be grounded just downside, so you bend it. The printed board is, let's say, 1 millimeter in thickness, so you have those 2 pads going downstairs, and you solder that well downstairs. But unfortunately, just this bent metal sheet is of, say, 0.25 nanohenry of inductance. You have 2 ones in parallel, so the resulting inductance is just 1/2. But that forms a good oscillator at, say, 26 gigahertz. So, I mean, even small inductances resulting from small connections between circuit elements might be a problem. And this is the description why the inductance effectively appears. It is a perfect chart, but shifted over a transmission line. Now, besides this comment, we will possibly talk a bit, or discuss that a bit later, how to handle that. We should now return back to the chart we have made. We have a chart with all possible values of reflections. Those reflections may range between plus and minus 1 in the real part, and between j and minus j in imaginary part. And just if we watch that, this is j omega l, so this is somehow, anything which is over the real x is somehow inductive, and you can get an imaginary part also, like so if you have something which is lower on the graph than the real x, it's somehow capacitive. Now we have this chart, and we could easily plot any reflection we wish. But there is another question, and this question is very important to understand. And we are slowly arriving to a Smith chart. By the way, Mr. Smith has invented the Smith chart, possibly by the same ideas I will tell you now. So we know that we have the reflection coefficients, but shouldn't we somehow join them to impedances that cause the reflection? Well, let's do that. So I will try to start with impedances, and I will use a red pencil now. So which impedance does cause a reflection of +1, exactly a real number 1? Well, that's an open circuit. So this point, which is a reflection of +1, is caused by a load impedance which is infinity. Now, which reflection is caused by a short? This is something we have already been discussing. So this is caused by an impedance of 0. Now we, at the time, already know one more point. There is no reflection, and that is caused by a load impedance equivalent to the impedance of the transmission line, to the characteristic impedance. So now we know 3 points that we can attribute both to reflections and to impedances. Now, if we investigate this equation, we could easily find out that, for example, there is a special circle and this circle has a special property. The real part of the impedance is equivalent to the impedance of the transmission line. Now there is a set of circles looking like this. For example, this is just 1/2 of this distance. This is a circle where all impedances do exhibit 2z0 as its real part. So those are circles of constant real part. We already have 3 on the chart. This 2z0, this z0, and this, which is 0. So let's add one more, which is 1/2 of z0, to have the system more or less looking like the one you can see on your Smith chart. So this would be. Now, as to the imaginary part, again, there is a set of lines. We have already one line that shows a constant imaginary part, at this time an imaginary part equivalent to 0, and that's the real x. So I could also draw it in red. Now, for example, at this line, it holds that the imaginary part of the impedance Z that is plotted is equivalent to Z0. And we would have a similar line or similar part of circle which has the same but opposite mark, opposite sign. So at this point we have 2 sets of lines. One of the set looking like circles that have their centers at the real x. This set represents circles of constant real part of impedance, of terminating impedance, and the red partial circles, upstairs and downstairs, represent constant imaginary part of the impedance. So now if I want, for example, to show a place where the impedance of 2z0 plus jz0 resides, it's quite simple. This is the line where the real part is 2z0. So it must be on that. And now we have the line where the imaginary part is z0. So it also must belong to this curve. So the intersection is the place where the picture is. So at this point we have an impedance of Z equivalent to 2Z0 plus JZ0. So now we can easily put impedances into the chart. But at the same time, we can easily read the reflection coefficient. The magnitude is given by this system of lines, and the phase is directly measured here. Now, this is not all. Mr. Smith has also had another question. Well, what about admittances? Well, and I will draw a green set of lines, which is, by the way, just mirrored around this axis. So if we have zero impedance, that means that the admittance is infinite. If we have infinite admittance, that means that the infinite impedance, then the admittance is zero. Well, of course, we have 1 over z0, that is y0, the characteristic admittance at the center of the line. And now we would get a similar set of circles. For example, this circle is a circle at which any impedance, any admittance with the real part equivalent to 1 divided by z0 or equivalent to y0 must sit. And there would be another circle for 1/2 of y0, and there would be another circle for 2 y0s. And as to the imaginary part, it would look like this again. Now those are not reactances but susceptances, but the story is more or less the same. And this is what you have in the Smith chart that I have shared with you through the Microsoft Teams group. And I will, for a few whiles, be commenting this. So it's a mesh of many lines. And in fact, what you can see on my whiteboard is that I have more lines or more types of lines that you have in the chart. Why? Well, in fact, in order not to have there 3 sets of lines, that is reflection, impedance, and admittance, only impedance and admittance are plotted. This is because those two are not linear. So it would be difficult to guess the values. On the other hand, the measure or the scale for reflection is linear, and therefore you do not have to plot it. You just know that the refraction magnitude is proportional to the distance from the center, and here it must be 1, and the angle you can measure just over here. And then it's quite simple to handle the chart. So you do not have plotted the reflection coefficient, but it's proportional, directly proportional to the magnitude and angle, so it's not plotted. What you have plotted there is the set of coordinates for impedance and admittance. Now, Mr. Smith used those two colors, red, like R, impedance or resistance, G, green, like admittance. And now, what is the benefit of so complex chart with so many circles? And that is a very complex question. First, I have to tell you that it evolved to a kind of language. And radio frequency engineers or microwave engineers just would not tell you a mathematical expression for the, let's say, evolution of impedance in the chart with frequency. They would just say, well, it copies the constant real part circle. So if you don't know the language, if you don't know the chart, you do not want what they tell you. The second thing is it has been very heavily used at times where there were no computers for calculations of impedances and reactances, and this is very easily aided by two colors. First, if you have to combine impedances in series, you add impedances, and therefore you use the red line coordinate system. In the case you combine impedances in parallel, you can't add impedances directly, but what you can add directly in parallel combination